So let me just recall that I gave two definitions of the Thurston metric on Teichmüller space. They are equal. I said this, they are equal for finite type surfaces with cusps and no boundary. In the case of this is a result of Thurston. In the case of surfaces with boundary, the definition should be modified, and I will talk about this later on. I want to mention two cases, two special cases, which are surfaces with boundary, in fact, and where this theory can be developed. This is the case I like very much, and I already talked a little bit about this. This is the case of ideal polygons. So most of the things I will say also today are based on ideal triangles. We know that we have ideal triangles. We know that we can glue ideal triangles, and the easiest way to obtain figures using gluings of ideal triangles is these ideal polygons. So we have this is an ideal quadrilateral. We can give it names. And the goal here, we can take an ideal. This is an ideal pentagon, and so on. And the goal for each ideal polygon with marked boundary points at infinity. First, we want to study the geometry of its Teichmüller space. This is a very simple example, in fact, but which I think is very inspiring, and it has not been done in detail. This is why I'm mentioning this. Study the geometry of its Teichmüller space equipped with the two Thurston metrics. So what are these two Thurston metrics? The first metric is so let's take the simplest case of ideal polygons. So ideal polygons exist only in hyperbolic plane. I don't have this in spherical or in Euclidean geometry. This is why this is. This is why it's interesting. This is why the geometry of ideal polygons is proper to hyperbolic plane, and it is the geometry of an ideal triangle is the basic thing which will come over and over again in all this theory. So we have these two ideal polygons, and then the distance between them, this is polygon A, this is polygon B, and then I have a fixed correspondence between the vertices. I know which vertex corresponds to which vertex. This is the marking. So this is marked ideal polygons. Marked ideal polygons. If I forget the marking, then I get something which is not the Teichmüller space, but the Riemann moduli space of ideal polygons, which is also interesting, but we are working with this now. And the distance between this one and this one is I don't need the half, logarithm of the best Lipschitz constant. Best Lipschitz constant of a homeomorphism f between these. I can measure distances. And then this is first version of Thurston's metric. The second version, if you recall, the second version of Thurston's metric used these lengths of simple closed geodesics on this surface, finite type surface with cusps. And here I want to replace these simple closed geodesics by just these geodesic arcs. These geodesic arcs. And here I have only two. Geodesic arcs which are distance minimizing between the edges. So I cannot take the distance minimizing geodesic arc between this edge and this edge, because the length of the arc will go to 0, in fact. But for these two opposite edges, I have a well-defined geodesic arc, which is distance minimizing. In fact, in the hyperbolic plane, this is just the length of the perpendicular, the unique perpendicular between these two geodesics. And I adapt Thurston metric to this, and I get a formula which is, well, the new distance is, there's always a logarithm. Let's give the names. This is G, this is H. Well, the supremum of log, the supremum of the length, let's say length with respect to G of this arc. This is the distance. This is the distance between G and H, and here I want to take H, and here the length for G of this arc A, and the supremum is over all the arcs A, and here I have only two, but in the case of a pentagon I have more than two. See, I have this one here, I have this one here, I have this one here. I never checked whether in this case of in this case of the Teichmüller space of the ideal pentagon, whether these two metrics are the same. Maybe they are the same. In first instance theory, in the case of surfaces of finite type with cusps, these two metrics coincide. Here, I don't know. Maybe they are the same. You see, when you double this ideal polygon, you get a surface of finite type with cusps, and then these arcs, they glue together and they give closed geodesics on this surface. Okay. Of course, on the surface you have other closed geodesics. On the surface, where you take the supremum over all the closed geodesics, you have other closed geodesics than these, but but maybe these suffice, because the type of surfaces you are getting are symmetric. In fact, they have, all of them has a two-order symmetry. Maybe these suffice. So I don't know. In fact, I didn't check this. I didn't write this. I didn't take enough time to think about this. If one of you wants to think about this, then it would be good. Anyway, if the metrics are equal, then this is already a result. If the metrics are not equal, then this is another result. And then you can study the geodesics for these metrics, the geodesic for this first metric, the geodesic for the second metric, and so on. The theory that we are developing now, the theory that I'm telling you for the case of surfaces of finite type, you can adapt it here. You can adapt it here and try to what extent you can adapt it. For instance, the fact that one of these, well, in Thurston's case, the metrics are equal and they are Finsler metrics. So you want to see whether these metrics are Finsler. You want to see whether how you can connect 2 points with a geodesic in the most economical way. If you find that it's Finsler, if you find that this metric is not a geodesic metric space, then you're sure that it's not a Finsler metric, and so on. I mean, this is an easy, easy to describe model for a space which carries a Thurston metric. So the second case, where you have also an elementary Teichmüller space. This is also the case of, I like these 4 letters. This is the case of a right-angled hexagon. Right-angled hexagon in hyperbolic space. Again, we have marked the vertices. We take the version of Teichmüller space is you are looking at maps between marked right-angled hexagons. If you forget the marking, then you get the Riemann moduli space, but let's stick to the Teichmüller space. And then here too, let me mention that these ideal triangles and the geometry of the ideal triangles, which is very simple, and the geometry of these right-angled hexagons, which is a little bit more complicated, will be studied. They are used again and again in the theory, in the general theory, which I will develop. But it is good to develop the theory, especially for these cases, and not only as tools to study the case of closed surfaces or surfaces with cusps. You can study these two cases for themselves, and here, okay, you have the parameters. So you want to define you want to define for the first version of the distance, best Lipschitz constant between two such polygons, 1, 2, 3, 4, 5, 6. F, you take the same definition as there. Yes, I didn't. Yeah, okay. Let me just mention that there's also a nice set of parameters, and this will be useful later also. Parameters for right-angled hexagons. This space is of dimension 3. This space is of dimension 3. So a different version, different kinds of parameters which may be useful, in fact, and which are useful in the general theory. First, let me remark that in such a hyperbolic right-angled hexagon, when I say three consecutive sides, I mean the lengths of 3 consecutive sides, like this one here. Let's call it LPQ. They completely determine the isometry type of the hexagon. So you can take these 3 parameters as the geometric parameters for the hexagon. So the proof of this is just a picture. The proof is just a picture. Let's think about the hyperbolic plane, the disk model of the hyperbolic plane. So I have, I have these three geodesics. This one, and this one, and I know. So this is P, and I know L, and I know this distance Q. And this completely determines the rest of the hexagon, because here I'm taking a perpendicular geodesic. Here I'm taking also a perpendicular geodesic, and then the third one is just the unique geodesic connecting them. This is not the most useful parameters these are useful parameters, but not the most useful parameters in the study of hexagon. There is another set of parameters which I want to mention here because they are important. They will appear in the later computations.
It's not true that any triple of positive numbers can be such a parameter because these two lengths can.
Yes, you are right. You are right. You mean this is this can be like this, and we cannot have the. Yes, you are right.
So there should be some inequalities.
Exact. There are some inequalities. This is correct. You are right. You are right. No, I want to keep this. Let's do this here. So there are some inequalities. But anyway, you have 3 parameters, and you can find the domain where these 3 parameters have to be. I mean, there's some interesting trigonometry here, hyperbolic trigonometry. The second thing The second set of parameters is the usual one, the most usual one, and it needs a formula. This is why I need my paper, because I never remember formulas. And here I have the names. I have called these sides M1, M2, M3, and then so this is S3, S1, S2, and the claim is that so three non-consecutive sides, any of the two triples of non-consecutive sides, so let's say M1, M2, M3, determine the hexagon. There is a geometric proof like this one, but it's more complicated, in fact. It's a little bit more complicated. I have to explain several things, but let me just throw in the formula, which is the usual formula that everybody uses. This formula, I use it in almost all my papers on the subject, in fact. But I never can remember it, in fact, because it's a formula, it's just a formula. This is cosh of S3. This is cosh of M3 plus cosh M1, cosh M2, and then here I have sinh M1, sinh M2. So I have a formula which gives me S3 in terms of M1, M2, M3. Okay, so I have the first definition of Thurston's metric, best Lipschitz constant between these. When you learn a little bit of the theory, then you will see how you can try to find the best Lipschitz maps between two such hexagons. You see, if I tell you again, if I tell you a very simple case of two rectangles in the plane, and I tell you what is the best Lipschitz map here, what is a best Lipschitz map, what is the dilatation, the least dilatation of a Lipschitz map, then you will immediately think of the affine map, sending this one, and then you are right. This is how you find the best Lipschitz map between this one and this one. Here it's a little bit more complicated. First, because here we use the construction and the proof that these are best Lipschitz map. You will use these. You will compute some derivatives and use these Euclidean foliations by geodesics. Here you don't have foliations like this. In fact, here what you hope to use is these foliations by equidistant curves, which are not geodesics. We already saw that equidistant curves to geodesics in hyperbolic plane are not geodesics, and here you have these equidistant curves, and then here you have equidistant curves. In these equidistant curves, you have perpendicular foliations by geodesics, perpendicular foliations by geodesics, perpendicular foliations by geodesics. So you have something like that, but then you must decide and try to understand what do you do in this middle non-foliated part. So the best Lipschitz constant computation here, I mean, is complicated, and it's a very interesting problem, I think, to find best Lipschitz constant between arbitrary ideal, not ideal. The ideal case was before, but here between right-angled hexagons. So this is for the first definition, and the second one. If I want to adapt the second one, then, well, I'm thinking of that definition there with these perpendiculars. So here I want to take also these perpendiculars. See, I have one here. You see, again, this perpendicular here is just the perpendicular between these two sides, the unique perpendicular between these two sides. And I say that this perpendicular between these two sides will stay in the interior of the hexagon. Because here I have a right angle. See, here I have a right angle, and then if the perpendicular goes outside my hexagon, then I will get here a hyperbolic triangle with two angles which are greater than two right angles, which is not possible. Okay, and so on. So the conclusion is that these three perpendiculars here, this one and this one and this one here, they stay in the interior of the hexagon, and then you can use them here to define this other distance. You have three parameters. In fact, we know that you have three parameters, and these three lengths should be sufficient to define a distance between the two hexagons. If the distance is if this supremum is 1, that is, if the length is 0, then the two hexagons must be, I suspect, in fact, I'm almost sure, I'm never checked this, they must be isometric and so on, and then you can develop this theory here. So this is a second interesting case where you can develop this theory. And you see, we talked about these foliations, which will be useful. We talked about these foliations, which will be useful. So let me recall that in the case before I erase this formula, in fact, it's not so complicated, but I mean, doing like you want to, typically you want to see whether this function is increasing or not in terms of this, and then you take derivatives, and the derivatives are very complicated in fact here, unless you are used to long formulas. But there are cases, in fact, which you can study. This is, for instance, the cases where M1 equals M2 equals M3, so you get special cases of one-dimensional version of these right-angled hexagons, and you can try to prove your conjectures first on this one-parameter family of hexagons. I didn't say, but this theory of pentagons also. Here you have a right-angled pentagon. It is less used in the general theory, but it should be also interesting in itself. I mean, the Teichmüller space of a right-angled pentagon, the Thurston metric, the geodesics, the description of the geodesics joining two points in this metric, and so on. The theory of foliations on this. objects, and this is what I wanted to recall, that on an ideal triangle, you have a canonical foliation by horocycles perpendicular to the boundary. They are centered at the pieces of horocycles are centered at the 3 points at infinity. And then I recall you that we have these K Lipschitz maps from one ideal triangle to itself by sending here a horocycle at length at distance x from this point to the horocycle at distance kx. Let's say that this is a big K. And then we said that you have either a surface with cusps divided into ideal triangles. You use these maps in some circuitous way. You use these maps to build K Lipschitz stretch lines. So these are let's draw it like this here. So this is Teichmüller space. And you get some lines here starting from one hyperbolic structure. You have to choose this ideal triangulation. You have to define the foliation by horocycles and so on, but this works well. And then you get some lines in Teichmüller space. You got some lines. So I drew them like this. There are obvious questions. Do these lines go to infinity in Teichmüller space? Do they converge to a specific point at infinity? So in this case, what does this mean? In fact, this is Teichmüller space equipped with its. So I equip it with a boundary, namely the Thurston boundary. But there are other possibilities of boundaries. Teichmüller space is by experience a space which carries a lot of structures. In fact, dozens of structures, and including several boundary structures, other than the Thurston boundary. But I will concentrate on Thurston boundary. And the question is whether these stretch lines converge to a specific point on the boundary, and the same question for these lines, which we call the anti-stretch lines, which are the stretch lines traversed in the opposite direction. So remember that this metric is not symmetric, and that these stretch lines, which, as we said, are geodesics for the Thurston metric, are not, in general, they are, in fact, in most of the cases, they are not geodesics in the other direction. And then you can ask about the behavior here. Does they converge to a point, or do they converge to a point, or do they converge to something else than a point? What is the adherence what is the adherence in the boundary, and so on. These are the good questions. I will, and this is what I want to talk about today. And then I told you there are some. I want to give a few references on this. So the main reference is Thurston's paper, the minimal stretch maps between hyperbolic surfaces. But what I'm talking about today about the behavior of stretched line, there are several papers here, and I want to tell you how you prove how you prove such a convergence here in the positive and in the negative direction. There are several papers, in fact. So Nikita, last day you asked about this question here. There was a foliation on this surface here, and then you asked how can this foliation not be perpendicular to, not be transverse to this foliation by to this decomposition by ideal triangles. And I told you, in fact, I told you that it could be the ideal triangulation itself, in fact, depending on what we intend by ideal triangulation, because the theory, as I said, works also for closed surfaces where the ideal triangulation is something which is not locally finite. It's just a decomposition of my surface into ideal triangles. Okay, and here you can have, I mean, you have to show that these exist. It's not obvious that you have such decompositions of the surface, but we will see we will see that they exist. And in this case, some measured foliations, you cannot represent them transversely. But in the case of a discrete triangulation, a discrete ideal triangulation, a triangulation obtained by decomposing the surface into a finite number of triangles using just these finite number of bi-infinite geodesics, then any foliation on the surface can be it can be made transverse to this. So I don't know if this was your question. In this case, yes. In this case, it's yes. Okay. So I wanted to give a few. So there's a sequence of papers. So Thurston's paper, which I already mentioned. This was written in '85. This question about the limiting behavior of stretched lines. I first wrote a paper on this. In the case of let's say finite ideal triangulation, like this one here, finite number of geodesics cutting the surface into ideal triangles. So this is a paper which appeared in 1988. If you are interested, you can Matematische Annalen, so you can look at it. But this is I will explain. I will explain this paper here, and then there's another paper which I wrote because I understood the general case, in fact, and not the case of this ideal triangle. And this is 3 years later. This is 1991 in in this is in topology and its applications. And then there's a series of 3 papers which I want to point out. These are papers by Guillaume Terret, which was who was one of my students, in fact, and I want just to copy the names of the papers because they are significant. The titles of my papers, in fact, I used to do this many years ago. The title, I don't know, it was something like on the hyperbolic geometry of surfaces or some very general title which is not informative. Now I learned that you must give informative titles. And so the informative title of the paper of Guillaume Terret is, this is on the negative convergence of Thurston's stretched lines towards the boundary of Teichmüller space, and this is in 2007. Okay, and so it tells you that he is studying the negative convergence, and his result is that when this ideal triangulation is itself contains a measured lamination, which all the other contains a measured laminations which carries a measure of finite support. You see, for instance, this in this example here, I can put a measure on this ideal triangulation, but it's not a finite support. This is the problem. But here, when this lamination carries a measure, transverse measure of finite support, with the rest of it being closed leaves, which geodesics, infinite geodesics, which spiral along these, this sublamination, which carries a transverse measure. Then these negative stretched lines converge. This is the result. The condition is a little bit complicated, but it's natural, and it's interesting. In fact, when you learn a little bit of this theory, which I will try to do. And then he has another paper. This is 2008, and this is called on elementary anti-stretched lines, and this is in Geometria Dedicata. He has a notion of elementary stretched lines, which generalizes a little bit what I told you before, and he shows that these anti-stretched lines converge. And then the last paper is called, in fact, it's in French, but I will translate the title in English. This is in 2010. And this is called Divergence and Parallelism divergence and parallelism of cylindrical stretch lines, and this is in algebra, geometry, and topology. So here he studies another question. In fact, not only the convergence towards the boundary, but the question is when do these you see, if you take a point in Teichmüller space and then you consider a stretched line, and another point, and you consider another stretched line, can they stay at a bounded distance? In fact, this is the question here. Parallelism. And he said the proof is, I mean, the result is yes, provided you consider this special kind of stretched lines which are where the foliations are cylindrical. In fact, the foliations are the surface is decomposed into a certain number of cylinders foliated by circles, and these are same kind of questions are studied in the more classical case of the Teichmüller metric. And when I say the Teichmüller metric using quasi-conformal mapping, this is a classical setting which I will not discuss here, but it has to do with the fact that this Teichmüller space equipped with the Teichmüller metric is not negatively curved. In fact, to study parallelism like this, this is part of the question of whether the fact is negatively curved in the sense of Busemann or in the sense of Alexandrov. In fact, since this metric is not a Riemannian metric, so you have to use these. When you study the curvature of this metric, you have to use the global definition of curvature, the synthetic definition of curvature with behavior of triangles, in fact, and not the local geometry in coordinates. Okay, so this is just to illustrate that there are many things which you can do with this metric, and again, in this, if somebody wants to study these special cases, then I think it's very interesting. Yes, so one question which I want to address is, you see, it's about these surfaces with ideal triangulations. Surfaces with ideal and I want to consider the simplest case. In fact, the simplest case is a surface the simplest case next to the ideal triangulation itself is a surface obtained by taking two ideal triangles and then gluing them pairwise. What do I get? I get a sphere. I get a sphere with. Well, topologically, it's a sphere with three distinguished points. This is well, three holes, a sphere with three holes. This is the first triangle. The other triangle is the complement of this one. Okay, so the question is, geometrically, what do I get? What do you think I get geometrically? As a hyperbolic surface, what do I get? I want to give a recipe to construct hyperbolic surfaces so that we know what we are talking about. You see all the theory we are developing. I want to have a picture of these surfaces, how they are constructed. So what do I get here?
It looks like three cusps.
Okay, so So I can get. This is correct. One possibility is that I get this, right? A surface with a sphere with three cusps geometrically, but in fact, it's not the only thing I can get. It's not the only possibility. The possibility is the other possibilities. You see, this is a possibility. I can get a surface like this. Pair of pants, a surface like this, where the triangles here, they spiral along this boundary component, spiraling here. I will say a few words about this. Why do I get this? In fact, I can get this, and also I can get this also, in fact, and then I can also get this. This is a possibility. This is a possibility. Here I have a spiraling. Here I have a spiraling. Do you remember what is, I will explain now. Do you remember what is the area of an ideal triangle? How much did we say it is? Pi. Yes, pi. So since I can get this pair of pants with geodesic boundary as a union of two ideal triangles, this tells me in particular that this pair of pants, its area is 2 pi, right? It's equal to a union of two ideal triangles. I can get in many other ways this result, but this is a simple way of seeing this. So I wanted to do this as a small exercise because I want to recall this notion. We will talk about foliations, right? We said we will talk about foliations, and I want to recall this. I want to recall the existence of this horocyclic foliation, in particular the existence of these three distinguished points on the boundary of an arbitrary ideal triangle, and then when I do this gluing side by side of these ideal triangles, I have this here, this shift here between the adjacent distinguished points, this shift between the distinguished point of adjacent ideal triangles, which can be positive or negative. I mean, I can decide that the positive shear is when I look from this triangle to this triangle. Then I see it on my right-hand side, which is the same. When I look from this one to this one, I see it on my right-hand side. So this is a shift, well-defined shift, which can be positive or negative. And then I'm gluing this to this, and I'm gluing this to this to get something which is topologically a sphere with 3 punctures. And let me write this general result now. Let me write here the general result. So a surface, a hyperbolic surface, let's call it S, is obtained by gluing, a certain number of ideal triangles. And I look at a puncture. This surface has punctures. This surface has punctures because I'm gluing these ideal triangles along their sides, and then there's always a point where a missing point at infinity. I look at a puncture. So here, this is a puncture, and here the vertices of my ideal triangles abut at this vertex. And then the result is that the surface is complete in the metric sense. At this puncture, if and only if the foliations by horocycles of all these triangles abuting here gives a foliation by closed leaves around this puncture. So in other words, here in this simple case, I have a foliation by horocycles in this triangle. I have a foliation by horocycles in the back triangles. Supposing that these three are the edges of my triangulation, then if these foliations fit together nicely as foliations by closed leaves, then this puncture is complete. The surface around this puncture is complete. If not, then there's no other possibility than to get a surface which is not complete. And let's continue here. Let's continue where? Here. Then, so if not, then the surface is not complete at this puncture, and its completion is obtained by adding a boundary component. I will explain this. I will explain a little bit. Yeah, let me first. So in this. In this case, you see, you can imagine that if the theorem is correct, if this result is correct, I mean, if you believe this, and or if at least part of this theorem, you can see that in this special case, the surface is complete, that is, it is a sphere with three cusps if the three shifts, did I call this shift? Because sometimes I call it shift. If the three shifts are zero. If the three shifts are zero, then it means that I'm gluing this point to this distinguished point on the other side, and then by symmetry, these pieces of horocycles, they glue together and they give me a tube foliated by closed leaves. You see, if the shift is not zero, what happens? If the shift is not zero, what happens? If the shifts, you see here at this puncture, in fact, at these punctures, I have two shifts, one coming from this triangle and from this edge, and one coming from this edge. And this condition here, okay, let's do it. Let's do it a little bit more in detail. Let's do it a little bit more in detail. I will use this picture here. So. No, I want a bigger picture. I want a bigger one. I want a bigger one. So I'm gluing, suppose I'm gluing this. I'm gluing this. Here is my non-foliated region in these two triangles, and here is my first piece of horocycle. Suppose I glue it, in fact, with some shift, say S, to a horocycle like this. Okay, to a horocycle, not this one, but one situated at a distance, a hyperbolic distance S above this one. So something we know, I think I mentioned it either last time or sometime here, is that the length of this horocycle is much shorter than this one. You see, if you draw an ideal triangle in the hyperbolic plane, like this, upper half space model, then something we know is that this is a piece of horocycle. Now, if this is a piece of horocycle, say a distance S above it, then by the way, this piece of horocycle is equal to, its length is equal to 1. This is equal to 1 and this is equal to 1, but we don't need this. We don't need this. What we need is that this length here is e to the minus s times this length here. And this is, you can see this just by a computation. You see computation in the hyperbolic plane where using this distance ds square dx square plus dy square divided by y square. So when you go up, the hyperbolic distance becomes exponentially shorter than the Euclidean distance. Okay. So here I'm gluing this I'm gluing this piece of horocycle to this piece of horocycle at distance s, and then so on, and then this one I'm gluing it. So I'm gluing it to one here, which is above it. You see the total. I want the total shift to be to see whether this geodesic, this horocycle is a closed horocycle or not. I have to see where it returns after a second time. Okay, so this is glued with this at distance s above it, and then I want this other shift to be of the same length s, and then this is e to the minus s times e to the minus s, and so on. And so on, and the result is that I get a curve here. I get the union of all these horocycles. You see, if it shifts in the same direction, then in some direction, then it continues shifting in the same direction, and the result is that the length of this curve, which I am following, because it's a sum of exponential like this, the length is finite. Okay, so what I get is a curve on my surface, which is not a geodesic, but this is not important. A curve which is of finite length and which is going to infinity. So my surface is not complete. This is why my surface is not complete. So, and the picture. This is exactly this picture here. You see, when I said that the curve is spiraling along a boundary component, so this is one piece of my horocycle, and I'm gluing it to a piece of a horocycle which is this is perpendicular, which is exponentially smaller. And then when I come back here, I glue it to a piece of horocycle which is exponentially smaller, and so on. And this curve here, this curve constituted of pieces of horocycle is going to infinity with finite length, and this is what I get. I get this picture here. You see, there's a simpler, maybe there's another way to see this. Let me draw another picture. So here I'm looking at the picture of the gluing of the two ideal triangles. But what I can do is to see what happens. You see, constructing this hyperbolic structure on this surface by gluing this triangle and then again this triangle. I can see it in the plane, in fact, like in the universal cover of this surface that I obtain. Which I know is homeomorphic to a sphere with three punctures. So here I'm gluing this ideal triangle in the universal cover. You see, I have here. I'm gluing this Euclidean line to a Euclidean line which is smaller, right? So my next, my next ideal triangle here is this one. My next ideal triangle is this one, and then I continue. This is called the developing map. This is a developing map of my structure here, and developing it in the hyperbolic plane. And then again this, I'm gluing it to this one here, and then I'm gluing it to one which is even smaller. So this is necessarily like this, and so on. Okay, and here I have a convergent sequence. This is the convergent sequence. The sequence of these lengths is convergent, so I must stop somewhere. So here I must stop somewhere. And the completion of what I get is obtained by adding this geodesic, which gives me this closed geodesic here. I want also to make another remark concerning this. I mean, here you enter into this combinatorics of shift parameters and how you get surfaces with boundary or surfaces with cusps or mixed cases by gluing. Here I'm gluing two ideal triangles. You can do the same by gluing three ideal triangles. You see, so let me say two things. The first thing is that when I take two ideal triangles and glue them side by side to get a sphere with three punctures. I showed you one way of doing it, but there's essentially one other way which can be split into three ways. So the first thing, first I can glue. I can start by gluing this side to this side, right? And I get what? I get something like this, which is this side, and then this is this side glued to this side, and then here I have so this is one of my triangles where I glued this side to this side here, and then the other side is okay. You see, this is my, and I can do the same for the other one. Same thing for the other one. Getting this something like that. And then I glue this part. This is the part open in the air, right? And this part open in the air, and I glue them together, and I get again a sphere with three punctures. Okay, and I have exactly the same discussion at these punctures. This is so the sphere. This is one puncture, and this is the second one, and this is the third one. And the general result is that whether it is for this case of the sphere with 3 punctures or for any other surface obtained by gluing ideal triangles, the result is that at each puncture I look at the sum of the shift parameters. The sum of the shift parameters that I see that I've used on this puncture. So, for instance, here I will have at this puncture I will have four shift parameters, right? This one here. In fact, I will have 3, but I count them as 4 because this one is counted 2 times. Okay, this one is counted 2 times. Plus, I have one coming from down and one coming from up. So I have, say, if this is delta 1 is the shift parameters associated to this side. Delta 2 is the shift parameters associated to this side, and then delta 3 the shift parameters associated to this side. Then here I will have to look at 2 delta 1 plus delta 2 plus delta 3 and the absolute value, because delta 1 is counted twice. So if this is 0, so this is 0 if and only if the structure, the hyperbolic structure, is complete at this puncture and I get a cusp. And this is different from 0 if and only if structure is not complete. So this is now a tautology, but furthermore, and the completion is a boundary component. And the length, this is the thing which I am adding here, the length of this boundary component is exactly equal to this sum. 2 delta 1 plus delta 2 plus delta 3. So I can get so you see the result I'm telling you here is that the result I'm telling you here is that the length of boundary component is obtained from the shift parameters by a very simple formula. If you understood a little bit how this theory works, how this theory of surfaces, hyperbolic structures on surfaces, and so on, then you know that the very elementary I mean, the most basic methods which are used here are those where I cut the surfaces into these pairs of pants, and then I analyze whatever I want, geometry of my surface or something more complicated on this pair of pants, and you see which are the simple surfaces, and now we know that well, each pair of pants, whatever, is completely determined by the gluing of two ideal triangles. Then I mean, the philosophy below all this is that the ideal triangles are even the simplest pieces of my hyperbolic geometry. You see, and then we have reasonings. I mean, you know that a hyperbolic pair of pants. A hyperbolic pair of pants is determined up to isometry by its side lengths. So the side lengths, we know that the side lengths are determined by the shift parameters of the two ideal triangles. Let me mention this fact also, since we talked about at the beginning of the lecture today, we talked about hexagons, and we saw this fact that a right-angled hexagon is determined by the lengths of three consecutive sides, but also three non-consecutive sides. There's this fact which I want to recall here, and which will be very useful. So we know how to decompose now a pair of pants into two ideal triangles, but there's this more classical fact that a pair of pants is decomposed into two right-angled hexagons, and this will be very important. In fact, I always draw the pair of pants like this, but it should be drawn like this, so that it resembles more to a pair of pants, right? And I mean, there are different shapes of pairs of pants. Let me draw. You see, we saw that the area of a pair of pants is constant, equal to 2 pi. And here it's not like what you said for hexagons. Here I know that I can choose any positive triple of numbers, triple of positive or zero, any three non-negative numbers for the boundary lengths of this pair of pens, because here they are the non-consecutive edges. What you say concern the consecutive edges. Okay, here I have no conditions, and the area is constant. So in fact, I could have a huge length of boundary components, but the area must be constant. So here I want to make it even. So if this is very, very long, then this will be like that. This will be like that. And the third one will be like that, so that the pair of pens is just like this. Right? So I like this picture. It's called a bikini, in fact. I learned this word from Sullivan several years ago. So you see, even if the pair of pens is very, very large, then this is like this. Even if the length of the boundary, you still, I mean, the meat is the area should be exactly equal to pi, and this includes also this includes the case where the area is zero in this formula here. Where the shifts are zero and the lengths of the boundary components are zero. This is my first remark, and the second remark was that we said that when you glue two ideal triangles like this, or I showed you there are three other ways, in fact. First, gluing this to this, or this to this, or this to this, and so on with symmetries. You get a theory with three punctures, but of course, when you glue two pairs of two ideal triangles, you can get a sphere with one puncture, right? Whose geometry is a little bit more interesting than the geometry of the sphere with three punctures, because because the topology is different. The surface is not simply connected, so its topology is more complicated and its geometry is more complicated. So for instance, I'm gluing this to this, and then I glue this to this, and then I glue this to this, and then I get either a punctured torus if the sum of the shifts here is zero, or I can get a torus with one boundary component where the length of a boundary component is the absolute value of the sum of the shifts arriving here. So this is the hyperbolic geometry which I wanted to do, and now the next thing is the convergence of the stretch lines, but this needs some time, and I will do this next time. I'll surely start with this next time. The theorem about the convergence, because I have to recall what is the Thurston boundary. I have to recall the general notion of convergence to a point on the boundary, and then tell you how you prove these results on the convergence of the stretch line to points on the boundary.